Okay, welcome to the first video of a new semester. This first one, we're going to be talking about network optimization models. This first video will cover a lot of the vocab, as well as introduce some of the main models that we'll be meeting this chapter. So network optimization models, the big idea is that we're building networks and then doing linear programming on those networks. And so what do we mean by a network? Really, it's just kind of a modeling construct that's just really, really helpful and useful. And it consists of nodes and arcs. So nodes, we'll kind of label, kind of follow the kind of convention of labeling our nodes with letters of the alphabet. Nodes are sort of your junction points. And then between any two nodes, you can have a arc or a edge or a link. There's a couple names for these things. So we've got nodes, sometimes called vertices or vertex. So that's a node there. And then between them is an edge or a link, or sometimes you'll see them called arcs. Okay, and network is just a collection of a bunch of nodes and a bunch of edges or links between them. And so here, I'll put another one in here and I'll connect these two. Okay, sometimes these arcs or edges will be directed, in which case then we'll sort of put an arrow denoting the direction of flow. Sometimes they'll be undirected, and so then direction doesn't really matter. And so, yep, these nodes here, maybe our typical example is that our nodes represent sort of sources of product, and some nodes represent sinks of products or where there's demand. And so some of our nodes will be supply nodes, meaning that they create goods. Maybe the easiest thing to think about is that these networks represent the movement of goods. And so supply nodes create goods, and I'll follow the book's convention of any supply that we create, we'll put in square brackets. And so maybe we're making 10 units of goods at node A, and I'll kind of put that next to that node. Demand nodes, they consume goods. And so maybe there's 5 units of demand, and I'll follow your book's convention and that demand is negative. Be aware that other books and other sources kind of might switch the convention there, and that's perfectly fine. Okay, so demand is negative, supply is positive, and so this one's creating 10 units, this one's consuming 5 units, and then in our network optimization models, we'll usually choose the flow along an edge to be our variables. Okay, and so here I'll say variables are the flows along the edges. And in our kind of standard example, that's the flow of goods, but it doesn't have to be the flow of goods. It can be the flow of money or just about anything. A lot of times it's not even quite what you'd consider a flow, but by kind of clever use, you can come up with a network model, even in scenarios where it doesn't quite fit the example of supply and demand. Okay, so we've got supply nodes that create goods, demand nodes consume goods. There's one other type of node which doesn't create or consume, and those are just called transshipment nodes. And they don't create or destroy goods. And so they have no supply or demand. Okay, and they're usually representing some pass-through point. Maybe there's a splitting where it could go from A to C and then on to another node D, or maybe it could go on to another node E. Okay, and maybe D has a demand of 2 units, and E has a demand of 3 units, so that we use up all of the supply that's coming from A. And so C is a transshipment node, B, D, and E in this scenario are all demand nodes, and A is a supply node. Okay, our variables, what we're usually looking for to solve for is how much goods should flow along each edge. And so I'll have one for the edge between A and B. I'll have another one for XAC, which represents the flow from A to C, XCD, and XCE. Okay, and this simple setup, it's not hard to sort of kind of by inspection determine what the flow should be to match up our supplies and demands, and that we should have 5 units flowing here, the other 5 units flowing here, and that splits into 2 units to there and 3 units to there. And so if it's this small of a problem, you can do it yourself, but oftentimes these network optimization models get very, very large. And so we'll kind of set up kind of what these look like and everything that we can do with these, and then let them loose on much larger problems where we couldn't just solve it by inspection. So our variables go on these edges. The other thing that's usually associated with the edges is most of the time we associate some cost with each edge. And so in the kind of standard example of supply and demand, it's usually the transportation cost. Okay, and so maybe I'll follow the kind of concept of putting numbers next to those edges that represent the cost for that edge. And so maybe this is 3, and that would be cost per unit transported. Okay, so it's a per unit cost that we have on each of these edges. And so maybe this has a cost of 2, a cost of 5 here, and a cost of 7 there. Okay, and a standard problem would be to minimize the total cost of transportation. Such that we follow the rules of kind of the rules of the network. And the main rule of a network is that inflow equals outflow. So I'll kind of say such that inflow equals outflow at each node. Okay, so we'll have a bunch of constraints, one constraint for each node that enforces what comes in goes out. And so things coming in might be supply or edges. So this edge XAC is coming into C. Things that go out are edges or demands. Okay, and so we'll essentially balance this equation at each node, and we might be wanting to minimize the total cost of transport. And so in this case, it would look like we'd want to minimize 3 times XAB plus, I've got a cost of 2 on XAC plus 5 XCD plus 7 XCE. So I've got 4 edges in this network. These are the 4 costs. So those costs show up in the objective function. And then at each of the nodes, I'm going to balance inflow equals outflow. Okay, and so at node A, I'm going to get a constraint that says what's flowing into A. Well, the inflow is 10 units of supply, and the outflow is XAB and XAC are both flowing out of A. And so I'd get 10 as the in equals XAB plus XAAC. And then at node B, the inflow is XAB, the outflow is the demand of 5 units. Okay, in this case, I'm writing it as a positive 5 on this side of the fraction, or on this side of the equality. So I tend to like to set up things as kind of thinking inflow, outflow, put all my ins on one side, all my outs on the other side, and then treat them as positive quantities, and then rearrange things at the end. I find that much more straightforward to keep my head straight on, rather than trying to remember our positives or negatives, ins or outs, demands or supplies. At node C, we've got XAC coming into node C, and we've got XCD and XCE coming out. At node D, we've got XCD coming in, and out we've got 2 units of demand at node D. So that's coming in, the 2 is coming out. And then XCE equals 3, in that XCE comes in, and we've got a demand of 3 at node E. Okay, and so we get 1 constraint for each of those nodes. Okay, and we see right away that, okay, XCD is 2, XCE is 3, XAB is 5, and then once I know these are 2 and 3, then I know that XAC is 5, and plugging them into this one, it turns out that we sort of satisfy everything. And so there wasn't really any optimization going on, just kind of solving for the missing values. Most of the time in the network, you've got a lot more connections than you have nodes, and so there's a lot of sort of degrees of freedom that you still have. In this case, we had more nodes than we had connections, because we actually had what's called a tree here, where we didn't have any loops or anything going on. And so there wasn't really any ambiguity on how the goods had to flow through this network. Okay, maybe the last thing I'll say is by way of kind of other key terms in these sorts of problems, is that the edges or the arcs can have a cost to them. They can also have a capacity. And so sometimes we'll have ranges of values that are the allowable value for each of those arcs. And if that's the case, then we get some extra constraints putting on essentially upper bounds or lower bounds on the flow of one of those variables. So essentially upper bounds and lower bounds for those specific variables. Okay. So that's sort of a brief introduction to network models. In the next videos, I'll introduce several different examples of problems that we can tackle with network models, and some of which we've seen before. So if you thought this example looked very similar to our transportation problems, it is essentially a transportation problem. And the way maybe to think about these network optimization models is just more general scenarios of your transportation problems, and we can apply them to a lot of other things. So that's kind of the introduction to the key terms. There's a little bit more about these key terms and other key terms also in chapter 10.2. So I encourage you to read that section to get a little bit more details there.